In this video, we discuss signal multiplexing. Multiplexing is a technique to transmit multiple signals in one channel. Think about a radio station. It can transmit different kinds of music, jazz, country music, or some news at the same time. And how do we achieve that? That is the technology of signal multiplexing come from. Multiplexing can be achieved in different ways. One of them is frequency division multiplexing. This is a channel, say from 100 megahertz to 110 megahertz. This is a channel I auctioned from FCC. Frequency division. So division means divide this frequency into a small portion, and each small portion can transmit one signal. And this is called frequency division multiplexing. The other multiplexing technique is time division multiplexing. This is a TDM. We separate the time into small portion. At each portion of the time, we transmit one user, say from T1 and T2. And I separate this time into smaller portion such that this portion I can transmit user 1, and this portion I can transmit user 2, and next portion I can transmit user 1 again. TDM has been used in our system, in current transmission system, and in practical systems, FDM and TDM actually used in combination together. Let's look at the conventional telephone system in North America. In early days, the telephone system normally we transmit voice message. The voice message normally have a few thousand Ks. To be safe, we confine the message occupy 4 kHz. The spectrum will like this, the voice, and like this is probably 4K, and this is 0 DC. It's a minus 4K. Okay, this is our message. Human being voice have very, very low amplitude strength in low frequency. Think about the singer. The singer, they can produce much stronger low voice signals than non-singer people. Okay, so anyhow, we assume that a voice message has this type of spectrum. In the telephone system, we use single sideband modulation, which means that we only transmit either upper sideband or lower sideband. Okay, suppose we transmit upper sideband. And how this been done? First of all, it groups the signal of 12 voice signal together and modulate, and then group another 12 voice signal to another group, and then they modulate the group again. It's called hierarchy scheme. But let's not talk about group modulation. Let's talk about this 12 voice signal from different users, how they've been modulated, use the frequency multiplexing. Remember the single sideband modulation. Suppose this is 0. And this is FC. And this is FC plus 4. This is kHz. And then the lower sideband we didn't transmit because we use a single sideband. So therefore, what is this carrier? This carrier must be here. This is the carrier, first carrier. And then of course there will be another one, minus FC. Yeah. Right. And then this is minus FC minus 4. See, this is single sideband modulation of this signal here. We want to organize all the signals in the frequency domain for different users such that we group 12 of them together. So each user occupies 4 kHz, 4 kHz, 4 kHz, and 12 of them. And we need bandwidth of 48 kHz. So we need 48 kHz channel to transmit these 12 voice signals at the same time. Now let's look at the diagram for the frequency division multiplexing. And this is a diagram. We have different users message, M1T, M2T, and I'm sorry for the blur, this thing. And total I have M12, maybe from this example. Okay, and first I pass this low pass filter. This low pass filter, the cutoff frequency is 4K. I make sure that message does not contain frequency component higher than 4K. So, and then this is each message will come in filtered by this low pass filter. Each message will pass through a low pass filter. And then we're going to do modulation. It depends on the single sideband modulation or double sideband modulation, whichever the modulation scheme, it doesn't matter. So there is a carrier F1, F2, and then F12. And in this case, if single sideband modulation being used, this is F1, this is F2, this is F3, this is a carrier frequency. And after that, we sum them together. After in frequency domain, if we add the signal together, we can see clearly in frequency domain that their spectrum of the modulated signal does not overlapping. But in time domain, that's different story. But in time domain, T, we only see U1 T plus U of 2T and plus all together. You will see a very, very messy, the high frequency signals. Very messy. We cannot do too much in time domain. But if we look at frequency domain, it's very clear the spectrum of the first message modulated is here. And the second modulated signal is here. Right? The third one is here. Once we sum them up, we can transmit through a channel. And suppose this is my channel. I transmit, and then at the receiver, suppose I have ideal channel. This is a whole signal I received. It contains all of the signal in frequency domain. So to extract the signal for the first user, the receiver for the first user, we need to pass through a bandpass filter. Bandpass filter, it only filtered out this portion. So therefore, this bandpass filter has to be related to carrier F1, the first carrier. And then after that, we do demodulation, demode, and then low pass filter, and then we obtain the first message. And then we do the same thing for the second user. We apply bandpass filter to filter out this portion. Look, this is a bandpass signal. It's still high frequency. And then we need to demodulate. Demodulate, you multiply by the same carrier depending on the scheme we're using. If we use single sideband suppressed carrier, Hilbert transform, we need multiply. We use multiplier to multiply the same carrier with the same phase. Then we pass through a low pass filter. We can obtain the message for the second user. And we do the same thing for all the users. This is the frequency division multiplexing system, how it works. So this is the diagram. So this is a diagram. Okay, not waveform, not spectrum, it's called diagram.